Let's start today's class. So we had started the subject of fluid mechanics from the last lecture. So just to summarize what all things we studied. So fluid mechanics is a subject that deals with the study of the behavior of fluid either at rest or in the motion. So in this subject, basically we are studying the behavior of fluid, which is if it is at rest, then we call it as fluid statics. Or if it is in motion, then we can call it fluid dynamics or fluid mechanics, whatever you want to call it. So these were all the topics that are included in the GATE syllabus. And these are the references from which you can find the detailed lectures from the NPTEL website. So a fluid you can call a substance. Fluid is a substance that continues to deform under the application of the shear force. So in case of a solid, if we apply the shear force, then it will resist the deformation and there won't be any permanent deformation in case of solid until a certain level of shear force. But in case of fluid, so the fluid will keep on continuously deforming when the shear force is applied. So that is how we define fluid. And this property of the fluid, due to which it applies the resistance to shear force, is known as viscosity. And the equation or the correlation capturing the viscosity of the fluid with that of the shear force applied, we can call it as this power law model, and it is given by this equation. So ultimately, this tau is dependent on the that is the shear stress is dependent on viscosity and the strain rate, that is tau is proportional to strain rate, and the proportionality constant we call it as viscosity. So this equation is valid for Newtonian fluid, and if any fluid doesn't obey this equation, then such fluids are called as non-Newtonian fluid, and they follow this power law model, where this first term m dvx by m dvx upon dy raised to n minus 1, we call it as apparent viscosity, and this equation is known as apparent power law model. In few of the numericals we saw, so using this equation, we had to find either the viscosity or the shear stress for the given system. And based on this value of n, we can comment on the rheological behavior of the fluid. That is, over here we can see that if n is greater than 1, then it is a dilatant fluid, and if n is less than 1, then it is a pseudoplastic fluid. And similarly, this for all the graphs. Then in fluid statics, we studied this basic equation, that is minus of del P plus rho g is equal to 0, which we can also write in terms of gradient as this 3 equation, which you can also integrate to find the pressure due to a fluid of height h as Pa is equal to rho g h. This also we can write. So this is the pressure due to the fluid of height h. If this is the height of the fluid, then at the bottom over here the pressure will be rho gh due to this portion, and if atmospheric pressure is acting Pa, then the total pressure will be rho gh plus Pa. So based on this equation, we will be solving few questions today. So these were few questions that we are planning to solve. So we discussed all the questions related to this viscosity or the power law model in the previous classes. Today we will be dealing with the static pressure. So this we will discuss after. Okay. So meanwhile, if you have any doubt, you can just unmute yourself or write it in chat box. Even if I am not audible or slides are not visible, you can just unmute and ask the doubts. So let's begin. So the first question that we are solving is a fairly simple question. It is question number 9 of GATE 2013, and I think it would go of 1 mark. So the question is, an open tank contains two immiscible liquids of density 800 kg per meter cube and 1000 kg per meter cube as shown in figure. If G is equal to 10 meter per second square under static condition, the gauge pressure at the bottom of the tank in Pascal is dash. So over here, we have been given a tank of this, you can say, semi-conical shape, over which on the top we are having air, then we are having a fluid of density ρ2 is equal to 800 kg per meter cube, and at the bottom we will be having the denser fluid, that is ρl is equal to 1000 kg per meter cube. So the fluid with density 1000 kg per meter cube is filled up to 1 meter, and the fluid with 800 kg per meter cube is filled from height of 1 meter to height of 3 meter. That is the total height occupied by the fluid to ρ2 is 2 meter. So we have to calculate the gauge pressure at the bottom of the tank. So gauge pressure, we can write it as gauge pressure is P absolute minus of P atmospheric. This is the gauge pressure. Basically, the difference between the atmospheric pressure and the absolute pressure is known as gauge pressure. So in order to find it, we can just simply use this P absolute from over here. So Pg is equal to, so the P absolute will be the total pressure acting at this reference level of H equal to 0. So from the atmosphere, we will be having the atmospheric pressure PA, that is P atm, atmospheric pressure. Then there will be pressure due to this fluid of density ρ2, and that pressure is given by EA is equal to rho GH. So since the density is 800, you can write it as 800. G we have been given in question as 10 meter per second square, and the height is 2 meter. For the density with, for the fluid with density ρ1, we can write this as 1000 into 10 into 1. So this pressure is due to the pressure due to the fluids present above the height h equal to 0, basically due to this two fluid and atmospheric pressure. And since we have to find this gauge pressure, we have to subtract atmospheric pressure from it. So ultimately, the gauge pressure will become, this P atmospheric will get subtracted out. It will be 16,000 plus 10,000, that is 26,000 Pascal. So in the question, we have been asked to write the gauge pressure in Pascal. So we can report the final answer as 26,000 Pascal. So that is our final answer, 26,000. Now the next question is also similar to the previous one, but the dimensions of the tank are different. And in this question also you can see that since we had to calculate the pressure, the dimension of the tank won't matter. Even if it is conical, even if it is decreasing, the dimension of the tank won't matter. However, if we were asked to find the force acting at the bottom, then this dimension would play a role. Now let us solve this question number 8 from 2016. So this question states that a vertical cylindrical vessel has a layer of kerosene of density 800 kg per meter cube over a layer of water of density 1000 kg per meter cube. L-shaped glass tubes are connected to the column 30 centimeter apart. The interface between the two layers lies between the 2 points at which the L tubes are connected. The levels in centimeter to which liquid rise in the respective tubes are shown in the figure below. The distance of the interface from the point at which the lower L tube is connected is dash. So in this question, first of all, we are given a cylindrical tank. So this is our cylindrical tank. And on the bottom, water is filled and the density has been given as 1000 kg per meter cube. And above water, there will be less dense fluid, that is kerosene, and its density is 800 kg per meter cube. And then we are given these two L-shaped glass tubes that are placed 30 centimeter apart. So the distance between these two tubes is given as 30 centimeter. And then we have been given the levels to which the liquid rise in the respective tube. So in this top L tube, the fluid is filled up to 20 centimeter, and on this bottom L tube, the fluid is filled up to 42 centimeter. And the location of this fluid, the lower fluid, is at X distance below the interface of kerosene and water. So this X we have been provided, and then we have to find this distance X. So to solve this question, we can consider this as our reference. And then we can write the pressure balance on the left side and the right side. So that if this is our left side and this is our right side, then we can write the pressure balance equation on both the sides. That is PL should be equal to PR. So we can write PL is equal to PR, and our main task is to find this X. So for that, we need to find the heights of the fluid and up to which both of these liquids are filled. So see, above this level of h equal to 0, the water is filled on the left side till x distance, and the head of the kerosene we don't know. So it will be, so this much is 20, since, and this entire thing is 30 and this is x, so this much will be 30 minus x. So you can say that the kerosene is filled to 20 plus 30 minus x height. And on the right hand side, since we are considering this as the reference, we will only consider this arm, and over here the height is 42 centimeter. So now we can use this information and write the pressure balance. On both the side, let us assume that the atmospheric pressure is acting. P atmospheric plus pressure due to this kerosene, so it will be, density is 800, so density is 800 into gravitational constant g into the height of kerosene, that is 20 plus 30 minus x, and then the pressure head due to this presence of water, and it will be, density of water is 1000 kg per meter cube, 1000 into gravitational constant g into height of x. And on the left hand side, we are having water filled up to this height of 42 centimeter. So it will be atmospheric pressure plus density of water into g into 42 centimeter. So we are keeping all these units in centimeter only, because ultimately this PA will get cancelled out and there is no point of converting this into meter, since that 100 will anyway get cancelled out. So we can simplify this and now find the value of x. So this g is also common on LHS and RHS, so we'll cancel that out. And on simplifying, we will be having 800 into 50 minus x plus 1000x is equal to 42,000. And this will be 40,000 minus of 800x plus 1000x is equal to 40,000, 42,000. This will be 200x is equal to 2000. So from here we will be getting x as 2000 upon 200 is equal to 10. And since this height was in centimeter, so this 10 is also in centimeter. That is, we can say that water is, the location of this below L pipe is from the height of 10 centimeter below this kerosene fluid interface. So the value of x is 10 centimeter. So the final answer, we have to write to the first decimal places, so we can simply report the answer as 10 centimeter. I hope both the questions are clear. If you have any doubt, you can just write it in chat box or unmute yourself and ask. So now let's take a look on this question number 23 from GATE 2019. So in this question, we have been given for a hydraulic lift with a dimension shown in figure, assuming g equal to 10 meters square, 10 meter per second square, the maximum diameter d left that lifts a vehicle of mass 1000 kg using a force 100 Newton is dash. So this is a fairly easy question and kind of very basic one. So over here on the left hand side, we are having a tube of diameter d left that is unknown, and we are applying a pressure of 100 Newton in order to lift a vehicle of weight of mass 1000 kg. And on the right hand side, the diameter of the cross section of the tube is 2 meters, and we have been asked to find the diameter on the left hand side. So over here we can simply use the Pascal's law. That is, basically we can just equate the pressure on both the sides. That is, P left is equal to P right. So pressure is force upon area. that is F1 upon A1 is equal to F2 upon A2. And on the left hand side, the force is 100 Newton. And the area will be pi by 4 dl square. Similarly, on the right hand side, the force will be mass into g, and that is mg, and it will be 1000 into 10. 10,000 Newton on the right hand side, and the area will be pi by 4 diameter square, and diameter is 2, it will be 2 square. So we have to find the d2, so this will get cancelled out. Z. So d2 square will be 4 upon 100. So d2 will be 2 by 10 is equal to 0.2 meter. So the diameter on the left hand side is 0.2 meter, 20 centimeter, but in the question we have been asked in meter, rounded up to 2 decimal places. So we can just write the answer as 0.2 meter. So that is our final answer of 0.2 meter. So this was a fairly easy question. Now let's take a look on a bit lengthy or a little complicated question. So this is question number 38 from GATE 2020. And the question is, a U-tube manometer contains two manometric fluids of density 1000 kg per meter cube and 600 kg per meter cube. When both the limbs are open to atmosphere, the difference between the two levels is 10 centimeter at the equilibrium as shown in figure. The rest of the manometer is filled with air of negligible density. The acceleration due to gravity is 9.81 meter per second square, and the atmospheric pressure is 100 kilopascal. How much absolute pressure in kilopascal has to be applied on the limb P to raise the fluid in limb Q by another 20 centimeter? So we will take a look on the video solution for this question. We are solving question number 38 of GATE. Due to gravity is 9 kilopascal. Let's just call it as. So in this question, we have been given two fluids. Let's just call it as fluid A and fluid B. For fluid A, the density is 1000 kg per meter cube. And for fluid B, the density is 600 kg per meter cube. And then we have been given this diagram where at equilibrium, the difference between the heights of both the liquid is 10 centimeter. Now we haven't been provided the height of this fluid with lesser density, so this will be fluid, let's just call it as B, and this will be fluid A. So we haven't been provided this height, so first we need to find this height, and then we have been asked that how much amount of force is required, how much amount of this pressure on P side is required to raise the height of this fluid B by 20 centimeters. So if this level is to be increased by 20 centimeter, what should be this force that we have been asked to find? So for first, let us find this value of the height. So let's just consider this interface as our reference level. and at this reference we can say that we write the pressure balance at this equation at this reference level. So from this reference, the height of this will be h, and this will be h. For this fluid B, the height will be h plus 10. So we can write this as Pp plus rho A G h is equal to Pq plus rho B G into h plus 10. Now in the question, we have been also given that both the limbs are open to atmosphere. That is, this Pp and Pq both will be same and equal to atmospheric pressure. So we can cancel that out. This G will also get cancelled out. And then we can find the value of h from over here. So rho A is 1000 times of h is equal to 600 h plus 10. This will become 1000 h minus 600 h is equal to 6000. So the value of height will be 6000 upon 400, that is 15 centimeters. So this height h is 15 centimeter, and this will then become 25 centimeter. Now we have been asked to find the pressure when we are rising this level by 20 centimeter. So since we are increasing this level by 20 centimeter, the level on this side will decrease by 20 centimeter, and the value of h was 15 centimeter. This was 25 centimeter. So let's just draw a schematic for this case, for which the height is increased by 20 centimeter. This was our initial reference that we had considered. Now, since the level will decrease by 20 centimeter on this side, so the new reference will lie 15 plus 5, it's 5 centimeter from below this surface. So this is 5 centimeter, and the fluid A will start from over here. And let's say it will go until this point, and this fluid B is until here. Now we are rising the level from 20 centimeter from above this. Okay, so this will become 20 centimeter, and since the height was 25 centimeter for this fluid B, this will be 5 centimeter, and for this the fluid A will rise again 20 centimeter on this side, because this B is also rising 20 centimeter. So this A fluid will also rise by 20 centimeter from the initial surface. So from this surface, the fluid A will rise by 20 centimeters. So this is our fluid A, and this is our fluid B. So over here you can see that the height of the fluid B was 25 centimeter, and in this case also it will be 25 centimeter. And since the fluid B, we are increasing the level by 20 centimeter, the fluid A over here will also increase by 20 centimeter. And corresponding to that, it will show a decrease of this level on the left side. Now for this case, we will write the pressure balance. So now we are applying the force of PP over here. that we have been asked to find. So PP is equal to, now what else we have been given? We have been given that atmospheric pressure is 100 kilopascal. So basically the ATM is 100 kilopascal. So at this level, we are writing the pressure balance. So it will become PQ plus rho A. So this is again 5 centimeters. Over here also it will be 5 centimeter. So the height of the fluid A on the right hand side is 20 plus 5, that is 25 centimeter. So rho A 25 into G plus height of this B liquid is rho B 25 into G. Now PQ, on this Q side we are having this atmospheric pressure of 100 kilopascal, so that we can write it as 100 kilopascal. Now we need to change the units of this two term also in kilopascal. So rho A was 1000 kg per meter cube into 25. Let's just consider it in convert it into centimeters. It will become 0.25 into G is 9.81 plus rho B is 600. Height is 0.25 to G is 9.81. To convert it into kilopascal, we will just divide the entire thing by 1000. So we can solve this and we will get 100 kilopascal plus, so this entire term will become 3.924. So this pressure that has been required will be 100 plus 3.924 will be 103.924. So this means that to increase the level of fluid B by 20 centimeter, we need to apply a pressure of 103.92 kilopascal on this P side. So the final answer from the given option, we will select it as option B. This option B is our correct answer. I hope that question related to manometer is also, this question related to manometer is also clear. So in this we were given this two fluid and we were asked that if I had to increase the height of this fluid Q by 20 centimeter, how much pressure should be applied on the left hand side? So first, for the given system, we just write the pressure balance and calculated the height. Considering this, we calculate this height, considering this as our reference level. And once we had this height, we just calculated the new reference level by considering 20 centimeter rise of this fluid Q on the right hand side. And over here, the fluid A will decrease in level. So it was around 5 centimeter from here. And now using this information, we again write the pressure balance and calculated this P. So now we will be solving some questions related to this fluid mechanics. So we are not diving into this vector notation of these equations. So we will be simply using this energy balance or the equation of continuity. So the energy balance will we'll be using the Bernoulli theorem for calculating all those parameters related to this energy balance, and we will be also using the equation of continuity to solve the next few questions. So this is question number 32 from GIT 2013, and the question is: water is flowing through a nozzle as shown below and exiting to the atmosphere. The pressure between the diameters of the nozzle at location 1 and 2 is d1 is equal to 4d2. The average velocity of the stream at location 2 is 16 meter per second, and the friction loss between location 1 and location 2 is 10,000 Pascal. Assuming steady state and turbulent flow, the gauge pressure in Pascal at location 1 is dash. So in this question, we have been given a nozzle where we are considering these two reference point of 1 and 2. At point 2, we have been given the fluid velocity, average fluid velocity of 16 meter per second, and we haven't been provided this velocity v1 at this point 1, and we have been asked to find the gauge pressure at location 1. So over here, we have been asked to find the gauge pressure. So the first task that we will do is we will be using the Bernoulli's theorem to calculate the pressure at this point, and then we can change it into gauge pressure. So let's take a look on the video solution again. We are solving question number 32 of GATE 2013 chemical engineering paper. At location 2 is 16 meter per second flow. So in this question, we have been given a nozzle through which water is flowing with a density of 1000 kg per meter cube. So at this location 1, the diameter is d1, and at location 2, the diameter is d2. The average velocity of the stream at location 2 is 16 meter per second square, that has been given, and the friction loss between location 1 and location 2 is 1000 Pascal. So friction loss, we can write it as 10,000 Pascal between 1 and 2. So we have been given turbulent flow and have been asked to find the gauge pressure at location 1. So we can use the Bernoulli's theorem to find the pressure at this first point, and then we can just change it to gauge pressure. So according to the Bernoulli's theorem that is obtained from the energy conservation, we can write this Bernoulli's theorem as P2 minus P1 upon rho plus rho H2 minus H1 plus 1 upon 2 alpha, where alpha is factor accounting for turbulent or laminar flow, V2 square minus V1 square plus summation of all the forces of the friction losses plus the work done. This will all be equal to 0. So over here in this question, we are not gaining any elevation while the fluid is being transported. That is, no height gain is observed. So we can equate the second term as 0. Similarly, no shaft work is done on this fluid in order to transport it to other level. So we can say that shaft work is also 0. Then this summation of F, we can write it as this friction loss. Now, ultimately, we have to find this value of P1. And the other thing that we don't have in this over here is this value of V1. So we can find the velocity of V1 by using the equation of continuity. So from the equation of continuity, we can write that rho1 A1 V1 is equal to rho2 A2 V2 the density of the fluid will remain the same since it is an incompressible fluid. So we can cancel this term. The area at this point, location 1 is pi by 4 d1 square. Velocity we have to find as v1. Area at this point is pi by 4 d2 square, and the velocity we have been given as 16. So this will get cancelled out, and v1 will be d2 upon d1 whole square into 16 square. So over here we have been given that d1 is 4 times of d2, that implies d2 upon d1 will be 1 upon 4. So it will become 1 upon 4 whole square into over here we are only having velocity, so this is not square, this is also not square, into 16. So v1 will be 1 upon 16 times of 16, that is 1 meter per second square. So v1 we obtained it as 1 meter per second. Now other thing that we have to find is friction losses. Over here we have been given that the friction loss between location 1 and location 2 is 1000 Pascal. So that is, we can write the friction loss in terms of this P by rho as 10,000 upon rho, that we can write. So now we will replace the value of V1 and this friction loss in this equation, and then find the value of this absolute pressure at P1. So that will become P2 minus P1 upon rho plus half times of 1 upon 2 alpha V2 square minus V1 square plus F we found out as 10,000 upon rho is equal to 0. Now we can replace all the values over here. So P2 we haven't been given anything about this P2 minus P1. So we can write this as P1 minus P2 is equal to 1 upon 2 alpha rho V2 square minus V1 square plus 10,000. Since we have been given turbulent flow, that implies alpha will be 1. Then we can replace the values of density. Rho is 1000, V2 is 16, and V1 was 1 plus 10,000. So this will become 256 minus 1 is 255. 255,000 upon 2 plus 10,000. So we will be having P1 minus P2 as 137500. Now we have to find the value of P1 gauge pressure, and these are ultimately we can say these are the absolute pressure. So that we can also write it as P1 gauge minus P2 gauge is equal to 137500. Now if we look at this second point, that is P2 gauge, it will be P absolute minus P atmospheric. Now since at this location 2 the fluid is already exiting to the atmosphere, the pressure at this point will be equal to P atmospheric. So this P2 gauge will be equal to P atmospheric minus P ATM is equal to, it will become 0. That is, we can write that P1 gauge will be simply equal to 137500. So the final answer, we can write it as 137500. So in this question, we used Bernoulli's theorem to calculate the gauge pressure at this point 1. And the only thing to remember in this equation is the Bernoulli's equation. And additionally, you can remember that if the fluid is exiting to the atmosphere, then the pressure at this point, the gauge pressure at this point, P2G, will be 0. So this thing you need to remember, or else you can just simply use this Bernoulli's theorem to find the pressure or velocity, whatever thing is asked. Also over here, the value of alpha was taken as 1 since the flow was turbulent. And if the flow is laminar, then alpha would have been provided, or it is usually 0.5 in most of the cases. Rest all was easy. Now let's solve few more questions related to this vector notations. So this is question number 48 from GATE 2014. And in this question, we have been given in a steady incompressible fluid flow, the velocity distribution is given by this equation, where v is in meter per second and xyz are in meter. In order to satisfy mass conservation, the value of constant p is dash. So since we have been given that the mass conservation is satisfied and also the fluid is incompressible, we can say that the continuity equation will hold true in this case. And here we have been provided the vector form of the velocity. So we can use the vector notation for the continuity equation. So that is, we can write this as del dot v is equal to 0, where we can write this as del rho by del t plus rho vx plus rho vy by y plus rho v z by z. So you can simplify this continuity equation in this form, and since we have incompressible fluid, the density won't change with time, and this term will be 0. And this Vx, Vy, Vz are the velocity components in x, y, z, or the I, j, k direction of this velocity v, that we can replace it. So del by del x, Vx is Vx plus del by del y, Vy is minus of Vy plus del by del z, and Vz is 5 times z. So this 3x minus py and phi z are the components of the velocity in xyz direction, and we have to differentiate them with respect to x, y, and z according to this equation. So once we differentiate it, it will be 3 minus of p plus 5 times z is 5. So this equation will hold true, and from this we can get the value of p as 8. So that is what we were asked in this question, the value of constant p. And from over here, we can see that it is 8. So the final answer, we can write it as 8. Now, Let us look on one more question related to the same vector spaces. So this is question number 39 of GATE 2014, and the question is: an incompressible fluid is flowing through a contraction section of length L and has a one-dimensional steady-state velocity distribution given by this equation. If u naught is equal to 2 meter per second and length is equal to 3 meter, then the convective acceleration of the fluid at L is dash. So let's take a look on the video solution. That will make things more clear. We are solving question number 39 of GATE 2014 chemical engineering paper. And in equal to u naught 1 plus 2x upon L, where u naught is equal to 2 meter per second, length L is 3 meter, and then we have been asked to find the convective acceleration. Now, from the equations of motion, we can write the equation of motion for this system as del for the velocity in x direction. This is our x direction and velocity in x direction. We can write it as delta Vx upon del t is equal to delta Vx del Vx del by del t Vx is equal to velocity in x direction del by del x Vx plus Vy del Vy by del y plus Vz del Vx by del z is equal to 0. Okay, over here we are having Vx. So the first term in this equation is known as local acceleration. And the last three terms are collectively called as convective acceleration. Now in this question, we have been asked to find the convective acceleration. So we will find the value of the summation of these three terms. And we can see that the second term is del Vx upon del y, that is derivative with respect to y. And since the velocity that we have been given is only a function of this x, this entire term will become 0. Similarly, this del Vx upon del z, since it's a derivative with respect to z, it will also become 0. So the convective acceleration in our case is simply Vx into del Vx upon del x. That is the convective acceleration. We can write it as Vx is equal to del Vx upon del x. Now we can replace the value of which ultimately is Vx is u, so we can replace that value. It will become u naught 1 plus 2x upon L into del by del x u naught 1 plus 2x upon L is equal to u naught, we can take it at common, so it will become u naught square 1 plus 2x upon L, and this derivative will become 0 plus 2 by L into 1. So this is u naught 2 u naught square upon L into 1 plus 2x upon L is equal to ax. Now in the question, we have to find the convective acceleration of the fluid at length L. we will replace the value of x as L. It will become AL is equal to 2 U naught square L upon 1 plus 2 L upon L will become simply 1. So it is 3 plus 1 is 2. This will become 6 U naught square upon L. So the convective acceleration of the fluid at length L is 6 U naught square upon L. And we have to find the numerical value. So we can just replace the value of U naught and L. It will become 6 into U naught is 2. So 2 square will become 4. One length is 3. So 6 4 is 24 upon 3. It will become 8. So the final answer, we can report that the convective acceleration is 8 meter per second square. So we looked on this question in which we had to calculate the convective acceleration. So total acceleration of any fluid is given by the sum of the local acceleration and the convective acceleration. Local acceleration is dependent on this time, whereas this convective acceleration is relative to the direction in which the fluid is moving. So the second term of this equation of motion is known as convective acceleration, and using that we had find this convective acceleration of the fluid at length L. So do you have any doubts in any of the questions discussed today, or we can wrap up for the day? In the next lecture, again, we will be looking on few of this question related to this Bernoulli's theorem. And then we can move on to this friction factor terms and the other terminal velocity, all those equations. So the syllabus includes Newtonian and non-Newtonian fluid, transport properties, self balances including differential form of Bernoulli equation, energy balance, equation of continuity, equation of motion, equation of mechanical energy. So I think we are solving this question until this part. This friction factor dimensionless analysis, I don't think has been asked until now in GATE. Then we have to cover this flow through the pipeline systems, velocity profile, flow meters, all those parts, all these parts are remaining. So if you don't have any doubts, we can end today's session. Thank you for joining.